there's a patch over the South Atlantic where Earth's magnetic shield thins so much that satellites glitch and astronauts brace for radiation spikes. A spot so bizarre even NASA calls it makes no sense. This stretch, known as the South Atlantic Anomaly, is where the planet's defenses actually leak. If the world's navigation and surveillance systems cross it daily, what happens when the anomaly grows? Earth's magnetic field acts like a giant, invisible shield, stretching from the planet's core out into space. This field is constantly at work, deflecting high-energy particles, streaming from the sun in deep space. Without it, the planet's surface would be bombarded by radiation intense enough to threaten life and disrupt technology. The strength of this protection depends on something called magnetic flux density, a measure of how much magnetic force passes through a given area. Where magnetic flux density is high, the field is strong and effective at steering away charged particles. Where it's low, more of those particles can slip through. The field itself is generated by the movement of molten iron in Earth's outer core. As this liquid metal churns, it creates electric currents that produce the planet's magnetic field. Under normal conditions, field lines loop outward from the southern hemisphere, wrap around the planet, and dive back in near the north. This structure forms the magnetosphere, a vast bubble that surrounds Earth and acts as a barrier against cosmic and solar radiation. Most of the time, this barrier holds steady. Satellites, aircraft, and power grids all rely on the predictability of the magnetic field to operate safely. Navigation systems use it to find direction. Communication satellites orbit within its protective envelope. Even migratory animals depend on subtle cues from the field to find their way across continents and oceans. When magnetic flux density drops in a region, that protection thins out. It's in these rare spots that the planet's defenses become vulnerable, and the consequences ripple outwards through technology, biology, and daily life. Satellites crossing the South Atlantic Anomaly encounter a world unlike anywhere else in low Earth orbit. As they pass through this magnetic weak spot, their sensors and computers are bombarded by an invisible rain of energetic particles. The most immediate symptom is the single event upset, or SEU. A charged particle slamming into a memory chip, flipping a bit from 0 to 1. For mission controllers, these bit flips are not theoretical. They show up as corrupted data, sudden resets, or unexplained glitches in spacecraft logs. X-ray observatories like RXTE and XMM Newton have recorded sharp spikes in background noise during SAA passes, forcing operators to power down sensitive instruments. The Hubble Space Telescope routinely shuts off its detectors when entering the anomaly, losing valuable observation time rather than risk permanent damage. The International Space Station faces a different challenge. Every orbit, its crew, and onboard electronics are exposed to higher levels of radiation as the station sweeps through the anomaly's heart. Dosimeter readings confirm the spike. Astronauts receive a measurable increase in radiation dose during each transit, prompting careful scheduling of spacewalks and experiments. Engineers design critical systems with extra shielding and error correction, but even the best precautions can't eliminate the risk entirely. For commercial satellites, the trade-off is starker. Early Globalstar units, built with cost-saving commercial chips, suffered repeated failures and shortened lifespans after repeated SAA encounters. Operators learned to expect more resets and lost data whenever their spacecraft crossed this unpredictable patch of sky. In the South Atlantic anomaly, the rules of spaceflight are rewritten, not by distance or speed, but by the invisible forces boiling up from deep inside the planet. Deep inside Earth, a restless sea of molten iron flows around the planet's solid core. This churning motion acts as a dynamo, generating a magnetic field that wraps the globe. But the process isn't as tidy as a simple bar magnet. Earth's magnetic dipole is tilted about 11 degrees off the planet's rotational axis, causing the field to bulge and thin in uneven ways. Under the South Atlantic, the situation grows stranger. Here, scientists have discovered reverse flux patches, zones at the core mantle boundary where magnetic field lines, instead of emerging outward, plunge back into the core. These reversed patches act like leaks in the shield, allowing the field above to weaken. Geodynamo models and satellite data reveal that these anomalous regions drift gradually west and south, matching the slow migration of the South Atlantic anomaly at the surface. The underlying cause is connected to a vast structure deep beneath Africa, known as the African Large Low Shear Velocity Province. This mantle province alters heat flow at the core's boundary, shaping the flow of molten iron and stabilizing the reverse flux patches above. As a result, the shield in this sector grows thinner, and the anomaly continues to evolve, driven by the push and pull between the core's restless currents and the mantle's hidden contours. Magnetometer readings from satellites have traced the South Atlantic anomaly's evolution with remarkable precision. Since 2014, the European Space Agency's Swarm constellation has mapped the anomaly's boundaries and tracked its slow migration. These satellites measure the intensity of Earth's magnetic field from orbit, producing detailed heat maps that reveal the anomaly's contours and changes year by year. Swarm data shows that the heart of the anomaly drifts at a rate of about 0.23 degrees south and 0.34 degrees west per year. The region itself is not static. It has grown by an area nearly half the size of continental Europe in just the past decade. In some sectors, especially southwest of Africa, the field is weakening at twice the rate seen near South America. Swarm's time series maps highlight a recent bifurcation. What was once a single minimum now appears as two distinct lobes, each with its own trajectory. These findings confirm that the South Atlantic anomaly is not a fixed blemish, but a dynamic, growing feature, one that satellites and operators must continuously monitor and adapt to. Not all spacecraft face the same level of risk when crossing the South Atlantic anomaly. The most vulnerable are those operating in low Earth orbit, altitudes stretching from about 200 to 1,000 kilometers above the surface. This is the realm of Earth observation satellites, weather monitoring fleets, and a rapidly growing population of smallsats and CubeSats. These vehicles pass directly through the heart of the anomaly with every orbit, exposing their electronics to repeated bursts of radiation. Operators of these missions must weigh the trade-offs. Flying lower means better imaging resolution and reduced launch costs, but also brings more frequent and intense encounters with the anomaly's radiation. Satellites in medium Earth orbit, like GPS and many communications relays, skirt above the worst of the SAA's effects, though some still catch the edge of the danger zone during certain orbital inclinations. High-value scientific missions, such as X-ray telescopes and particle detectors, are especially sensitive, as even a single stray particle can corrupt data or trigger automatic shutdowns. The International Space Station, with its human crew and constant presence in low Earth orbit, sits squarely in the crosshairs, requiring extensive shielding and strict operational protocols. As the number of satellites in low Earth orbit continues to climb, so does the overall exposure to the Anomaly's unpredictable hazards. Each new mission faces a familiar dilemma: how much risk can be tolerated and what price must be paid to keep systems safe. Every satellite mission that crosses the South Atlantic Anomaly faces a series of hard choices. Shielding electronics against radiation means adding extra layers of material, sometimes aluminum, sometimes specialized composites. But every kilogram of shielding increases launch costs and limits the payload that can be delivered to orbit. Engineers must weigh whether to protect sensitive components with heavy-duty armor or accept the risk of more frequent failures. Radiation-hardened chips offer another defense, but they come at a premium. These parts are bulkier, consume more power, and can be several times more expensive than commercial off-the-shelf alternatives. In missions where every watt and gram counts, the decision to use rad-hard memory or processors is often a debate between reliability and budget. Some operators schedule their most vulnerable instruments to sleep during South Atlantic Anomaly crossings, sacrificing observation time to avoid permanent damage. Others rely on error-correcting code memory, which detects and fixes bit flips on the fly, though this solution increases power draw and complexity. Real-time monitoring of radiation levels is now standard for many spacecraft, triggering automatic safe modes when thresholds are exceeded. Each mitigation strategy comes with a trade-off: more mass, higher power demands, or lost data. Mission planners must constantly balance these factors, knowing that every shortcut could mean the difference between a successful mission and a multi-million-dollar failure. In the last 20 years, ESA's swarm satellites have measured the South Atlantic Anomaly growing steadily, now spanning over 8 million square kilometers and drifting westward by more than 20 kilometers each year. Scientists confirm that it's caused by the tilt of Earth's magnetic dipole and complex flows in the outer core. Yet the fine details of these deep Earth processes remain unresolved. For satellite operators, this weak patch means hardened electronics, higher costs, and scheduled shutdowns. Facts borne out by mission logs and engineering records. Despite decades of research, no model fully predicts how the anomaly will change in the future. What is clear: as global reliance on satellite navigation, Earth observation, and communication grows, the South Atlantic Anomaly is not just a scientific puzzle. It is a persistent operational hazard, one we must track, measure, and adapt to, as long as our technology orbits above this unpredictable zone.